Hi, we are Group 10 and here is what we will be talking about in this video. Let's start off with a video of the phenomenon in real life. Do you know why and how this happens? Today, we will share about the law of Bernoulli that is behind this phenomenon. Before we begin, we need to understand the law behind Bernoulli's equation. The Bernoulli equation was founded by Daniel Bernoulli, a Swiss mathematician and physicist who was studying about the laws of conservation of energy, where he established the Bernoulli equation from his findings. The law of conservation of energy states that energy cannot be created or destroyed. It can only be transformed from one form to another or transferred from one location to another. Bernoulli's equation reflects this principle by showing that the total mechanical energy of an incompressible, non-viscous fluid remains constant along a streamline. Bernoulli's equation is applied to the laws of conservation of energy, where we see a balance between three forms of energy per unit volume: pressure energy, kinetic energy, and gravitational potential energy. If one of these quantities changes at a point along the streamline, at least one of the other quantities must adjust accordingly to maintain the total energy. This results in an inverse relationship among these terms. For instance, if fluid velocity and therefore kinetic energy increases, pressure may decrease to conserve the total energy along the streamline. Well, what is the relationship between the Bernoulli equation and the phenomenon? Firstly, the flow at the nozzle will have the fastest speed and as it moves up and reaches the bottom of the ball. As the airflow travels upwards, the velocity decreases due to interaction with the surrounding air particles and reaches the stagnation point where the velocity is zero. According to Bernoulli's equation and law of conservation of energy, when the velocity decreases, the pressure increases, and when the velocity is zero, the pressure is the greatest at the bottom of the ball, generating an upwards drag force on the ping pong ball. As the drag force is large enough to counteract the weight of the ping pong ball, it balances the forces within the flow. This is why the ball does not fall off the flow. But even if the weight of the ball is balanced, what about the forces to the left and right, and why didn't the ball fall off the sides? Well, this can be explained with the Coanda effect. Firstly, when the airflow reaches the ball, it moves over the surface of the ball, where viscous forces and friction causes the airflow to stick to it, resulting in the Coanda effect. As the flow sticks to the surface, it follows the shape of the ball, curving around it. As the fast-moving air flows past the sides of the ping pong ball, the high velocity creates a low-pressure region. The low-pressure region around the ball and the atmospheric pressure surrounding it causes pressure imbalance. As the pressure is higher away from the ball, the force acts against the pressure gradient and towards the ball, keeping it in place instead of letting it fall off the sides. Thus, it keeps the ping pong ball within the flow. But why does the ball wobble side to side as seen in the video? Boundary separation occurs, and a pair of vortices is formed, A and B. They are unstable, and when exposed to small disturbances, vortex A grows larger than B and draws B across the wake. Vortex B cuts off further air supply to A, causing A to be shed. This alternating shedding causes an alternating pressure difference, resulting in a net force oscillating between left and right. This movement is called vortex-induced vibration. Now that you understand how this phenomenon works, can you think of any other examples where this phenomenon is observed in real life?